last time behavior. Now we look at combining functions. So doing algebra on functions. So basic operations on functions. So we have two functions, f and g. They have their respective domains, d sub f and d sub g. When doing arithmetic, how many operations do you have? Basic arithmetic. Right? Addition and multiplication are technically the two. But you also learn subtraction and division. You can also use those on functions. Sum of functions, you can add two functions together, create a new function, call it f plus g. It's just f of x plus g of x. And its domain is the intersection of the two domains. Which, if you think about it, makes sense. You can't add an undefined term. Right? So both functions have to be defined simultaneously. That's what the intersection says. Then you can take the difference of functions, f minus g of x is just f of x minus g of x. Once again, the domain is the intersection of the domains. Product of functions, f times g of x. F of x times g of x, domain, again, the intersection of the domains. And last but not least, you have division, quotient of functions, f over g of x. Just f of x divided by g of x. Domain. Intersection of the domains minus anywhere that the denominator is 0. So that's what that symbol is. That's set minus. That works fairly simply. What it says is look in the first set, in this case, the intersection of your domains. and remove the elements of your second set. That's all set minus is. Right, so those operations are not new. You're familiar with them already. We're just now applying them to functions instead of numbers. This next operation is new. Composition of functions. So you use the output of one function as the input of a different function. It's called the composition of functions. And for any input x, functions f and g, the result is called a composite function. Written as f open circle g. That's red. F composite with g. And its definition is just f of g of x. Domain of this new function can look confusing. It's the set of all x in the domain of g, such that g of x is in the domain of f. There will be a sixth operation that we look at. I don't remember if it'll be Wednesday or Monday. I think Wednesday is transformations. It'll be Monday, so next week. And then those will be the 6 operations of functions that we will be using. We're given 2 functions, want to find the 4 basic operations on them. Some difference product and quotient along with the respective domains. So we start with f plus g. Just f of x plus g of x. Adding fractions, what do you have to do?
Get a common denominator.
Common denominator. More specifically, you look for what common denominator? The least common. What is the least common?
X.
Just x. It's not just x. Do that. Least common multiple of 18 and 20. Do you remember how to find it?
You divide by
I think you're confusing LCM with GCD. The GCD, I agree, would be too. What are they teaching nowadays? Right, each in prime factorization. Eighteen is 2 times 3 squared. 20 is 2 times 5. Look at the first prime factor too. What's the highest power that occurs? We also have a 3. What's the highest power that occurs?
2.
What's the highest power that occurs for 5? There's your LCM. 2 times 3 squared times 5, which is 90. The least common denominator is the least common multiple of all the denominators. So the idea is the same. You want to write everything in its fully factored form. Then take the products of the highest powers. X is already fully factored. What about x squared minus 4? So it's x times x plus 2 times x minus 2 is your LCD. What do we have to multiply the first denominator by to get the LCD? So look at that first term, the denominator. What do you have to multiply it by to get our least common? So you also have to multiply the numerator by x. What about the second? So what do you have to multiply the second term's denominator by to get our least common?
X squared minus 4.
Means you're also multiplying the numerator by x squared minus 4. Now it's just a matter of simplifying. So there is the sum. Now for the domain. What's the domain for f?
Just for f of x?
Hmm?
Just for the
Yeah, just for f, what is its domain?
anywhere besides where x squared minus 4 equals 0.
Which means x can't be what?
0. 2.
Not for f. 2, what else?
-2.
And everything except for plus minus 2. What about the domain for g?
Anything besides where x equals 0.
0. This domain is the intersection of those two. So it's everything that the two domains have in common, which would be everything but -2, +2, and 0, right? So the domain. F minus G. You get to use instructor's prerogative. F of x minus G of x. Subtracting fractions is the same thing. You have to find an LCD, right? Which is going to be the exact same. So instead of plus 2x squared minus 8, we get minus 2x squared plus 8. Negative x squared plus x plus 8 is the difference. Domain is the same.
That for everyone, so we can do some, whether like
Except for division.
yeah, but for the addition subtraction.
In division, there's one extra step you have to do, and that's take out wherever the denominator is 0. Product is just f of x times g of x. What's the rule for multiplying fractions? Now cross multiply. Generally, that's if you're solving an equation. Which is an easier way to do that too. Just multiply straight across. And multiplication is nice and easy. And again, the domain is just the intersection, so it's the same. Quotient f over g. F of x over g of x. What's the rule when you divide fractions? Multiply what by the reciprocal of what?
The denominator.
You multiply the denominator by the reciprocal of? Numerator by the reciprocal of the denominator. So numerator stays the same. Now it's just regular old multiplication. There's the quotient. Domain is the intersection minus anywhere that g of x is 0. Well, the intersection we already know. Look back at g of x. Where does g of x equal 0? That's what we're solving for. 2 over x equals 0. Where is 2 over x equals 0? How would you solve that?
It's undefined at 0, never equals 0.
Yeah, there is nowhere it equals 0. If you were to try to solve this, multiply through by the LCD, which is x. wind up with 2 equals 0, which is nonsense. It's a contradiction. So we're subtracting the empty set. We take nothing out of the first set then. So the domain would be the same. Notice here, if all you do is look at this term, right, so you find f over g, and then you try to find the domain the standard way, wouldn't you just get x can't be plus or minus 2, which is the incorrect domain? That's why you have to go through this process. Now, if you don't include x can't be 0, then what you're saying is you can take f and divide it by a non-existent term. Specifically, you'd be dividing it by 2 over 0, which is not possible. So you have to go through that entire process. Let's actually start by finding the domains first, before I forget. So the domain of root 1 minus x. One to infinity. If x is 5, what are you taking the square root of? You allowed to do that?
No.
So you used the wrong inequality.
Negative infinity to 1.
Yeah, be negative infinity to 1. Right, what's under the radical has to be greater than or equal to 0. Now here it's more convenient to actually use interval notation. That's what I'm using. Remember, the two notations can be used interchangeably. What's the domain of G?
Oh wait, no. No, it's not. It's not. It's you can also do negative infinity
To 2?
to negative.
Negative 2. 2 to infinity is only half of it. Yeah, it's everything except what's between -2 and +2. F plus G, f of x plus g of x. Can that be simplified?
Can't use square root.
Wouldn't that change the values?
Yeah. So no.
So you can't do that.
So no.
Yeah, that can't be simplified. That's already fully simplified.
Subtraction, same thing.
So you just leave it like that. Domain.
But why do you write like upside down U?
That's intersection. That means set intersection.
Okay.
So it's where the two, which all the elements that the two sets have in common. Right. So think of a Venn diagram. Right. One circles A, one circles B. The intersection is where they overlap.
Okay.
So what do those two sets have in common?
Negative infinity.
I agree, negative infinity.
-2.
I agree. It has all that in common, right? Does it have anything else in common? No. Right, 2 to infinity would be greater than 1. Right, the first set only goes up to 1. And the second set doesn't have anything between -2 and 1. So there's your intersection, that's the domain.
And that's going to be the same for subtraction, right?
The domain will be, yeah. Right, difference. F minus g is just f of x minus g of x. Again, that can't be simplified. Domain is the intersection. It's the same as addition. One of the things that makes technology great. Just duplicate the slide and erase the plus and make it a minus instead of rewriting everything. Copy and paste the wonderful feature. F times g. F of x times g of x. Can that be simplified?
Is this when you can do what I said last time? Or still no?
What did you say though?
Like, take the square root of, or I mean square root.
Would still change the value, right?
Yes and no.
So no. If it changes the value, you're not allowed to do it.
Can you put it all under?
Multiplication distributes across the square root.
So make it,
So we can combine that as a single square root. And that can be simplified. And this negative x cubed. I'm going to have a plus x squared, a plus 4x, and then a minus 4. And FOIL and then rewrite the terms in descending order of power. You don't have to do that. That's just how I like to write them. There we go. And the domain's the same. F over G, f of x over G of x. Can that be simplified? And it's still going to give you the same answer.
yes.
I agree, no, it can't be simplified, but it can be rewritten.
Or you could put the whole root of
Yeah. So it's, do you want to write 2 square roots or 1? Is ultimately what it boils down to. Is one simpler than the other? Not really. Of course, if this was algebra, you couldn't keep it like that. And what they told you to do in algebra, if you have a radical in the denominator, yeah, you had to rationalize it. But this isn't algebra, is it?
You have to do anything with it, you have to put that, right?
Not necessarily. The whole point of simplification is it's the exact same thing. So you wouldn't have to.
But it's easier, right?
Yeah, it depends. So in this case, I'd say that is definitely the simpler form than rationalizing it. There are times where rationalizing it might actually give you a simpler term. So I'm just going to leave it like that. Don't have to rationalize it. And in general, this is how you would keep it in applications. Like in my physics courses, yeah, that's how we would keep it. Domains, the intersection minus everywhere that g of x equals 0. Where does g equal 0? So list that out. List the actual values. And I already said the intersection was that, right? So we take that interval and subtract from it the set -2, +2. So again, here's how set subtraction works, because now we don't have an empty set. Look at your first set, -∞ to -2. Is -2 in it? Remove it. Is +2 in it? Then we don't need to do anything. That's the domain.
So it's just still the same?
They're not the same.
Because it's a friend.
One was closed at -2, this one's open at -2.
Then why is it?
Because we're taking out -2,
So you can't do that.
right? That's what set minus is.
Uh,
So set minus says take this set, remove from it these elements. Since there was only -2 in there, we just removed -2. And that's the new set. That's what set difference is.
Change them to correct.
Because we're removing -2, yes. If -2 was somewhere in the middle, that would become a split interval. Right, let's say that was -∞ to -1. You have to remove -2.
so it becomes -1.
So go -∞ to -2 unioned with -2 to -1.
And you would still use parentheses with that?
In that case, yeah, because -2 is not included anymore.
Can you write that out? Just like, see, like, get the visual.
What, this one? That? Right, same interval, except we removed the -2 from it. That's set minus. I think when you first learn set theory, if I remember correctly, in algebra, they do it in terms of Venn diagrams. It does make it easier to visualize all of the operations. Composition. F composite G. Know what that means? F of G of X. Grab the domains again, whatever I'll do after this.
Wait, what does it circle mean?
Composite. What's G of X?
What, you're asking what the domain of G of X is?
No, just what is G of X?
X squared plus 5x.
So it's F of X squared plus 5X. Everywhere you see an X in the definition for F, replace it with X squared plus 5X. Can that be simplified? And factor it. Is that going to help with simplifying? So there's really no point. Just leave it like that. Oh, really? Not in this case, because I'm not using that definition to find domain. Back to the original functions. What is the domain of F?
Isn't it like bracket 6 to infinity?
What is the domain of G?
What was it in the bracket?
Isn't it? Is it negative infinity, -5, and then 0 to infinity?
Why?
What? Why?
Yeah.
It's like, I did it like x equals 0 plus 5, and x can equal 0 or -5.
Why can't they equal 0?
It's because it's equals 0.
Was there anything wrong with 0?
Oh, okay. Oh, so is it negative infinity?
Yeah, it's all real numbers, right? Domain. Set of all x in the domain of G, such that G of x is in the domain of F. In context of this problem, here's what that means. the set of all real numbers x such that x squared plus 5x is greater than or equal to 6. Right, because g of x has to be in 6 to infinity. We need to simplify that.
What are you asking for?
We have to simplify that domain now. Because how that's written is unacceptable. That can be simplified. So we have to solve this inequality.
You're right. X minus 6 is fine.
Not here. Right, so we have to use the breakpoints, set up test intervals, all that if we were doing it by hand. I don't actually have the space to do that. And really at this point, am I testing on whether you can solve an inequality? Not really, that's what algebra is for. So let's see how technology, let's see how technology helps. I should be able to do it on here. Maybe not. Crud. Just see. No, I can't. Okay, I think I'm going to have to do it from a graph then. That is true. So x squared plus 5x minus 6. Probably even, maybe, does the TI 83 and 84 do relations?
I don't think so. That's what's got to go.
Don't think it does.
That is not hard.
Mine does. Really nice. Remember, we're looking for greater than or equal to 0, right? So it'd be this portion up here and this portion here. So what does that intercept right there? Now this you can, I know the TI-83 does do this.
7.
And you analyze graph, you can find the zeros. Again, you have to axis greater than 0, right? And then 1 to infinity. Endpoints are included because you can equal 0, right? The inequality was greater than or equal to. So it's a set of all real numbers satisfying that interval. Well, everything in there is a real number, right? So that's our domain. G composite F. G of f of x. What's f?
Square root of x minus 2. Or 6.
G of square root of x minus 6. Look in G. Everywhere there's an x, replace it with square root of x minus 6. What am I doing? 5. Square root of x minus 6, all squared.
X minus 6.
Can that second term be simplified?
Just put 5 before it's 6.
There's the formula. Domain. Set of all x in the domain of f, such that f of x is in the domain of G. Well, domain of f would be greater than or equal to 6, right? So the set of all x greater than or equal to 6, such that f of x, square root of x minus 6, and what was the domain of G?
All the way around.
Such that the square root of x minus 6 is a real number.
That like E means like
Element of, in.
Yeah.
Right? In the case of a set of real numbers, you typically shorthand that as is a real number. when would the square root of x minus 6 be a real number?
What?
When would the square root of x minus 6 be a real number?
X is greater than 6.
Just greater than?
So the square root is 0.
What's square root of 0?
0.
That's a real number, isn't it?
And then here,
So just be x greater than or equal to 6. So in the case of this, it'd be everything. Ooh, look, both of them are square roots. That's nice. What's the domain of f? The all real numbers. X squared plus 5 can never be negative. In fact, the smallest it can be is 5. What is the domain of G?
negative infinities and negative 4, or negative 2 and 2 infinities.
Sure about that?
No. Oh, wait, no. It's 2 to infinity. No, it's negative 2 to positive 2.
Negative 2 to positive 2. Right, this one's 4 minus x squared, not x squared minus 4. Which means now x squared would have to be smaller than or equal to 4. F of G. Right, G of x square root of 4 minus x squared. Plug that into F. How would that simplify?
Well, square root 4 minus x squared. squared is negative x squared plus 9. Right?
Negative x squared plus 9 minus x squared, same thing.
Just leave it like that.
Because that can't be simplified any further, right? Domain. Set of all x in the domain of G. So it'd be the set of all x between negative 2 and positive 2, such that g of x is a real number, right? Such that g of x is in the domain of f. Where would the square root of 4 minus x squared be a real number? The answer is obvious. It's staring you in the face.
Between negative 2 and 2.
Between negative 2 and positive 2. Because it's just the domain of it, right? There's the domain of the composite. Look at the square root of 9 minus x squared individually. What is the domain of that? So what would the domain of the square root of 9 minus x squared be? Between negative 3 and positive 3. And of course, notice that is not the correct domain. Right? In fact, that would include an infinite number of points more than what we're allowed. Again, it's important to actually go through this process with composite functions and not just look at your end result and try and get domain from that. G composite with F. It's G of f of x. How would that simplify?
X squared plus
You drop something.
negative x squared subtract 1.
Now look at the domain. Set of all x in the domain of f such that f of x is in the domain of G, which can be broken down even further. Square root has to be non-negative, right? When you take the square root of something, you get a non-negative answer. So we cut this in half, basically. I'm going to write it out. How would you solve that? I'd square everything. Should I keep going? Guess so. Subtract everything by 5. What's wrong with that statement?
It can't work. Anything squared would be a positive.
This is saying that x squared is negative, which is not possible. That means there's no solution. There are no real numbers where the square root of x squared plus 5 will be between -2 and +2. The domain's empty, which means this isn't even a function. Let me rephrase that. It's not a real value function. That is a function. You just have to go into the complex plane to define it, which is definitely beyond the scope of the calculus. Now you could have determined that very easily just by looking at f and saying, well, the range is 5 to infinity. Right? The smallest value f can take on is 5, or I'm sorry, not 5, root 5. Square root of 5 is greater than 2. Slightly greater, but still greater. Which would have told you right away the domain's empty. So the toughest part is probably going to be finding domains. I say finding, I mean determining domains. Right, the algebra itself should be pretty straightforward. It's then just determining the domains that's probably going to give you your struggle. What we're about to do is extremely important. We've just looked at composing functions, function composition. What's the opposite of composing something? Decomposing. So we're going to be given a function, we're going to decompose it. Very important in Calc 1 when you study chain rule for derivatives. Very important. In fact, in general, it's all of Calc. Being able to recognize a function composition and decomposing it into its function components. We're going to find functions f and g such that the quantity of 5x minus 3 cubed is f of g of x. Now, theoretically, there's an infinite number of solutions. There's theoretically an infinite number of functions f and g such that f of g is 5x minus 3. I'm sorry, not cubed to the fourth power. In calculus, you generally want to find the simplest solution. F of g. F would be your outer function. G would be your inner function. Inner function. Isn't it just 5x minus 3? What are we doing to 5x minus 3? So there's f, x to the fourth. There's your decomposition. Again, it's not the only solution, but it is the simplest. So what about here? What do we think?
G of x equals 1 minus x squared.
What's that?
X squared.
What is it?
Square root of x.
There you go. That would be a decomposition.
Why is the square root of x?
Because you plug in g of x for x to get negative 1 minus x squared, which is
And so you understand why we got g of x to be 1 minus x squared? Let's start there. Yeah? What are you doing to it? taking its square root, right? So that's f, square root of x.
G of x, x squared minus 5x plus 6.
What would f of x be then?
1 over x to 2/3.
Or x to the minus 2/3 I would also accept. I tried. I've been trying all class. Like a tax advisor telling you how you should probably set money aside for your taxes, and then you don't listen. And they get shocked at the end when you owe taxes. Any questions?
So calculus one arrow, we're going to start with decomposing?
You don't start with it. When you get to the chain rule, that's when you start looking at this stuff. That's when this becomes very important. Also, the addition, subtraction, multiplication, division will also be important. Being able to recognize when you have a sum of functions, when you have a difference, a product, and a quotient. And being able to interpret what f is and what g is. Not necessarily combining like what we were doing, but recognizing what they would be. Anything else? And 10 minutes left. Let's see what I can find. So here we're given f and g. I'm not going to worry about finding the composition, just the domain. So let's find the domain of f of g and g of f without actually finding the formula for them. Start off. What is the domain of F?
6 to infinity.
Half of it.
Oh,
Wait for the after that.
Yeah, just F. What is its domain? Negative and negative 6.
Oh no, it's isn't it negative infinity to 6 and then 6 to infinity?
Everything but 6.
You got half of that, right?
I was looking at like,
Yeah. Sure.
If this was government work, you'd be close enough. What's the domain of G?
negative infinity to 0, 0 to infinity.
Everything except for 0. Domain of F of G. Elements in the domain of G so let's say all x not equal to 0, such that G of x is not equal to 6. Which would mean that 7 over x can't be 0, right? So where does 7 over x equal 0? Never. So there's nothing to really consider other than x can't be 0. Domain 4, G of F. Elements in the domain of F such that f of x is in the domain of G. Where does 1 over x minus 6 equal 0?
Yes. Oh wait, it's the same.
Nowhere. So there would be the domain. You have an assignment due today.
The 18th. You know, that is,
See you Wednesday.